Hello, hi. Just checking that everybody can hear me. James, are you able to hear me as well? Fantastic. Good afternoon, everybody. My name is Craig Donaldson and I'm the course advisor for the Electrical Power Systems Engineering course. I'd just like to say that we may be experiencing I may be experiencing some technical difficulties with the broadcast here. I'm not actually able to share my webcam. Hopefully you can see James Brooks's. He will also share the slides with you as well. Please do let us know on the chat feature or the questions if you cannot see us or hear us, and we'll do our best to fix that. Just before we start, obviously I've introduced myself. I'd just like to mention as well that James and I are working remotely at the moment, and that is due to the circumstances with COVID virus. So the university has taken the policy to close non-essential buildings, which does include James and I's building where we work from. So we are working remotely from our homes, as you can see. Okay, so the flow of this session, I'm going to hand over to James very shortly. He will run through the presentation. Please do send us questions as they pop to you. I will pitch these to James, and we'll do our best to answer them. And I think with that probably leaves me to hand over to James.
Yeah, and Craig, can you hear me okay?
Yeah, that's great. Thanks, James. I can hear you.
Excellent. Okay. Now we are sort of 1 minute beforehand, so I don't know whether we should give people who are arriving dead on the time just that last minute to set up. So, as I say, as we go through, please put down your questions sort of as we go along, and there'll be a chunk of time we've devoted at the end to answer them. But I'm happy to sort of answer questions and just put them down as you go.
Great. I'm just double checking, James, to see if we've had anybody raise concerns they can't hear us. I've got one person to say, it does sound like we're crystal clear. That's great news. Hopefully everybody else is the same as well. It looks to me as if we have around 22 attendees now. So I'm really pleased that everybody can join us.
Excellent. Okay. Well, I suppose we should get started then.
Great. Yeah, fantastic.
1 o'clock by my clock.
Yeah, same with me, James.
Good. Okay. Well, welcome everyone, and welcome to this webinar on electrical power systems engineering, the online version of the course. I'm the course director, and I'll be kind of running you through most of this. This one's focused on one particular aspect, one particular taught unit of the program, which is smart grids and sustainable energy systems. And a little bit of background on myself. I'm a senior lecturer with the university in the Department of Electrical Engineering, but I'm also the academic lead for pedagogy. So I have a real focus on how do we improve the quality of teaching, how do students learn, how can we make that more efficient, more effective, particularly within science and engineering. So you'll see sort of bits of that brought into the course, which I think is quite good for an online course where people maybe have been out of education for a little while. Back when I did my PhD, that was looking at quantifying the risks where you've got systems that have a really high penetration of renewable power. Basically, if you've got lots of wind turbines, does that mean the lights go out more? And the answer was, obviously, it depends. But yeah, that was what I used to research. And now I'm really focused on building and growing this MSc course. And in terms of kind of where the MSc course sits, at the top level, you've sort of got electrical and electronic engineering. And you can split that into the high power and the low power stuff. We ignore the electronics, we look at the high power, the generation, transport, and use of electricity. And then even within that, you could sort of split it into machines and components, you know, designing a steam turbine or designing a motor or designing some power electronics device. We don't focus so much on that. We're looking at the sort of the system view, the overall view of the network. And that includes, the components. How do you analyze them? How they operate? How do you operate them? What are the kind of asset management concerns if you've got a whole suite of transformers or lines? How do you monitor their reliability? How do you manage protection of those systems? And then the bit that we're going to talk about here is, what are the current innovations? What's the future trends? What's sort of the new things that are happening? So that's a sort of broad overview of where this course sits. It's that system view. And it's an exciting area to be in. There's this kind of a lot going on at the moment. In some parts of the world, you'll see kind of a real massive increase in electrification generally. And in others, you'll see a massive changeover. And maybe depending on what area you're working in, you'll have sort of seen this from a number of aspects. I see this as three main drivers, three main things causing this change. The first is this decarbonisation, this clean energy. And I think it's interesting that that's driven both by governments and by consumers, because that causes two different pushes in different ways. Then a separate sort of driver, a separate source of change is the technological advancements. So all the people that I said study, the machines, the materials, the power electronics, storage systems, of which the university has a separate research group that does that. They have an impact on the system as a whole, and we look at that impact of the system. And then there's an increase in the demand, or the way that power is, or energy is being used, and it's becoming more electrified. And that's sort of electrification of electric vehicles, rail, and then maybe combined heat and power systems, so electrification of heating. So that's sort of saying there's a lot going on, there's a lot of exciting things happening, but it makes the field a lot more complicated. And what you probably could say with that is there's a whole set of research that's going on of thinking about what those trends are and what those changes are. And we do talk about that briefly in this smart grids unit. But I'll come on to the detail of what's in it. And really, in terms of then the impacts, there's three different areas. And what I've said is smarter grids rather than smart grids, because really, if you talk to anyone who's been in this a while, all of this stuff that I've listed has been going on for a long time. You can't say that there hasn't been increasing demand over time. There is certain forms of storage. There is participation, particularly at the high voltage levels, the transmission system levels. But what we're seeing is that there's an increase in the complexity, an increase in the amount, and an increase in the complexity, particularly at the medium and low voltage levels, at the distribution system levels, where they have to operate really quite differently. And that's why this particular taught unit focuses on that, because it's an exciting area of change. So if I just go through these sort of three pieces, the changes to generation are mostly renewable, and the complexities there are, one, that the new generation is often distributed. So either it's, you've got a wind turbine connected very far away from a load center, which has some challenges, or you've got thousands of people putting solar panels on their roofs, which is so different geographically and then how it's connected to the network to having a single large coal or gas power station. It's also non-synchronous, so that spinning mass of a rotating machine like a coal or gas turbine adds to the stability of the network. It sort of buffers changes in frequency, and that lack of synchronicity, even for something like a wind turbine, because it's connected through power electronics, adds complexity. And then it's also non-schedulable. You can't tell a solar panel, I want more power now, in the way that you can with a gas turbine. You can just open a valve there. So that's the sort of complexity coming from that side. And then on the demand side, there's an increasing demand because more things are being electrified, although in some cases you'll actually see a reduction in demand through efficiency savings and through this increased participation. And that's probably one of the biggest changes, is that end users are getting more involved, or maybe I should say smaller end users, because you always had, large steelworks and the like signing contracts with system operators to be disconnected in certain sort of emergency situations. But now you might just see it as a cost saving or an option available to you as a customer to buy cheaper electricity at different times, to join in the market in different ways, particularly if you've got your own solar panels, your own electric vehicles, your own storage. So that's the demand side. And then that complexity, that extra control and options means that as a system, we see a lot more information and control available and complexity in that. And that moving everything to computerized systems brings cybersecurity risk. It also brings options for increased kind of computer intelligence, increased automation. So all of this is kind of under the realm of smarter grids or smart grids. And there was a recent paper out that kind of looked at a survey on different technologies, different applications of smart grids, and came up with a huge number of different things. So obviously for this kind of particular piece, we've had to focus on one thing, one particular area. And since this unit really isn't about policy, it's about, you know, what is the voltage, what is the power, what is the impact of all of these coming changes on the actual wires, on the actual devices, on the stability and security of the network. That's what we decided to focus on in this unit. So we split it down into 6 different sections, and I'll show you in a bit how they look. But the first one really is kind of what I've been talking about in the last 5 minutes or so. What are smart grids? What is this energy trilemma, this balance between the costs, the environmental impact, and the stability and security of the network as a whole? So we sort of discuss that. Then we start looking at more concrete impacts of low carbon technologies, and that brings us into some more kind of numerical calculations so we can quantify these in terms of costs, environmental impact, and so on. Then we talk about flexibility, and just as an example of flexibility, I brought an old example now, but it's quite a clear one to explain. So this is called the duck curve. This is an example of, I think it was 2016, looking at what the demand across a day was for a particular part of California. And you get sort of a gradual changing curve as people kind of wake up in the mornings or go home at night and use cooling and various different demands. But as you get more and more solar power being introduced as the years go on, and this was a sort of predictive model, you get less generation in the daytime because, or effectively less, it looks like there's less because houses are not requiring as much power from the sort of grid, from the whole network, because they're generating it locally. And that's great. That means that in the daytime, you can turn off, turn down coal stations, gas power plants, and all the others. And then as it gets to the evening and things get dark, you've suddenly got to massively increase them. You've got to open up all the valves and very quickly increase the power output of conventional generation. More and more so, the more sort of solar panels that you have, and that's a challenge. So do you have the ability to quickly turn on new power plants, or to open up the valve so you can increase the ramp rate, or the ramp rate's sharp enough that you can do that? And if you've got to have all of those generators up and running, then you have a problem in the midday period where you might not actually have, you might have too much generation there for the demand, which is a problem. That'll cause the frequency to increase. So you probably have to just disconnect some wind turbines, or turn the blade so that they don't produce anything. And that's just a complete waste. You've already kind of paid for setting them up. The power could be generated and you've just disconnected them because you have no other options. And these are some of the challenges of flexibility in low carbon systems. We'll talk about a lot of others and we go into a lot more detail, and there's some sort of calculations and kind of work to do in that. But that's the sort of first half. You're sort of setting the scene of what does it look like across the system. And then in the second half, we talk about where a lot of the change is happening at the distribution level, and what do low carbon technologies actually impact, and how big is that impact, and how can we mitigate that? And if I go on to an example of the coursework, so there's one bit of coursework that covers the first half of the unit. And that you're given the system on the right. So you've got a number of different generators connected to 4 different bus bars, different power flows between them, and you're told, optimize this. And what you'll find in the initial case we set up is, whatever you do, you have to switch off some wind. And then you've got this discussion or this open-ended problem of, what could you do about that? How can you change some kind of definition of how you protect the system, how you back up the system, the ramp rates, the way you coordinate and control the increase in energy over that kind of evening period, so that you can use the wind turbines. Because what you're finding is that because of the flows down the lines, you have to use the wind turbines. You have to disconnect the wind turbines and use coal somewhere else, which is a terrible solution, given that everything is set up so that you could use it more efficiently. And then that kind of continues on into a discussion of, well, what if we see changes to that system where we have tri-generation? So this, rather than separate, a power station produces your electricity, you've got a boiler in your house to produce your hot water and heating, and you've got an electric chiller in factories to cool down things. Couldn't you have a single thing that produces all 3? Because there's a lot of waste heat in a power station. And what would that look like, both from a cost, emissions kind of point of view on the system? So that's one of the projects. We use a piece of software called PowerWorld for that. And then the second one is, okay, what impact does that actually have on a distribution network? So if we pretend off at the left, there's that higher level transmission system, there's actually going to be a load of houses connected, individual houses. And those houses will want to connect solar panels, or they'll want to connect electric vehicles. And that's going to change the voltages at one of these bus bars, and those voltages might be out of limits. So you might have a problem where you say, look, you guys can't connect your solar panel because the system just can't support it. And there we start talking about active network management. We start talking about forming mesh networks rather than these kind of linear power flows from one point out across to the farthest point here from left to right. And you've got 2 separate channels. Can't we join those 2 endpoints up? Can we change the transformer on the left so that it can remotely work out what setting it needs to have so that the bus right at the end is still within limits? And how do you manage that? So that's another piece of coursework. So that gives you an idea of the sort of area of smart grids we picked for this, because it is such a broad topic. We also get you to do a literature review to sort of look at what's going on in the future. Can you research this area for yourself, because there's so much kind of coming up and changing. So that's kind of what the unit is as a whole. Then if we look at, that's just one example of one of these 8 taught units. So there are 8 units, each lasting a fixed period of 10 weeks. At the end of that 10-week period, for 4 of those units, you'll do a coursework-based assessment, like the one I've shown you. For 4 of them, you'll do an exam-based assessment, a written exam. Up to 4 of those units can be taken a year. So if you've got a particularly busy period in work, you can just say, well, I'll only do 3 this year, I'll take a little break. And that means for that taught period, 2 years' time, you should be able to complete that minimum. And then you start this big individual research project that's often tied up with what your job is at the moment, so that it benefits your employer, it benefits you, and we pair you up with an academic who kind of knows about the area. We are looking at actually sort of shifting this around a bit and seeing if we can bring that minimum time down, and that would make it a bit more intensive. And that's one of the things we're looking at for next year, not for this September intake. But that's the structure of the course as it stands. And then in terms of what the course sort of pages look like, this is one of the sort of snapshots of Blackboard, which is our learning management system. You can see those 6 sections there. And we're currently looking at section 5, which is the technical aspects of low carbon technologies. And if we kind of scroll down a bit, then you get this video worked example showing you, okay, you've got these 4 bus bars with power coming in from the left, going out to 100 different houses at bus bar 3 on the right, how many electric vehicles can you connect to that and still have an acceptable amount of power flowing through that transformer between bus 0 and bus 1. And this, you'll watch this 10-minute video, you'll see the solution, and that will really help you solve the coursework that I showed you earlier. Obviously, the coursework is a much more complicated problem, but this simpler one gives you that learning. Then there's a discussion activity around that to help cement that knowledge and sort of allow you to chat to your colleagues. Then further down, there's a link to the course text, which you can read online, that goes into a bit more detail and provides some of the kind of background information for that. What else do we do as well? Oh, every couple of weeks there'll be a live video tutorial similar to this, where you can sort of chat to your tutor who's assigned to you for this, ask questions, give feedback. But there's a lot of feedback as the course goes through via email and sort of submitting pieces of work for feedback and discussion there. Yeah, and as I showed you, we give you a couple of pieces of software as part of the course so that you can do these courseworks that we've shown you. So that's the course as a whole. Then why Manchester? Why choose this university? And I've started broad here. Historically, we've had 25 Nobel Prize winners who've been associated with us, which is a huge number, and a number of them are still here. We have a number of Nobel Prize winners, and a large percentage of our research was either world leading or internationally excellent. That was the last Research Excellence Framework statement. Last year, we were the University of the Year for graduate employment, and the last world rankings, QS rankings, said we were 6th best in the UK and in the top 30 in the world. And I'm hoping that when 2020 comes out and the new ref comes out, that we'll have improved on that even further. So we're a fantastic university, but if you look down specifically at the division that we're in, the Electrical Energy and Power Systems group, we're even better. We've got one of the longest, so the on-campus version of the course is one of the longest running, possibly the longest running power systems course in the world, established in the 60s. And a number of our researchers are world renowned and published many hundreds of papers, and are really excellent in their field and in many different areas as well. I think this is quite a strength of the course, is that we have people all the way from kind of, almost the chemistry of particular components and particular, oil degradation in transformers, to what does the power system in aircraft look like, to what would modeling the system of the future be, purely simulation based. There's a real variety of expertise. The students are another benefit as well. So these are sort of some of the logos of employers that have sent students on our course. Obviously, you've got large engineering companies, you've got a couple of oil and gas companies, and you've got transmission and distribution system companies as well. And it's nice that you get some collaboration and links with your sort of fellow colleagues. In terms of your entrance requirements, we require that each person on the course has a sort of first or 2-1 honours degree in something relevant like electrical engineering, or something that's equivalent to that. I know there's a whole system of international equivalencies there. We will factor in industrial experience, and we will, on top of that first or 2-1, look at the grades in the relevant taught units, because what we really want is to show that someone is at this first 2-1 level in the things that are relevant to this course. The power systems, maths, if you've done circuit analysis, control, a number of things that are relevant here. And then we'll look at the standing of the institution where you studied. We also need evidence that you're competent in English language. There's IELTS requirements there. There's further details that are available on the web for that. And the fees are 10.5 for UK EU and 25k for international. That's over the period that you'll study. So So that's total. And in terms of then what we need from you, the course is designed so that you spend an average of 15 hours a week devoted to this course for 40 weeks a year over the sort of 2.5 to 3 years that you'll take to complete the course. You must be able to take part in the video conference tutorials. Your computer has to be able to run the software. There's a question over the exam centres, but when they're all back up and running, when COVID is no longer an issue, you'd have to be able to physically attend the exam centres, of which we've got many around the world. Normally it's a British council or a university that we've partnered with. And then just as a sort of final point, going back to this smart grids unit, I thought some people might want to kind of read up on this themselves if it's an area they're interested in. And these are the sort of recommended course texts. So the smart grid by Bolan is where we start with that kind of overview. And then when we move into the later units, we're talking about distributed generation and the challenges of that. That was involving some academics back when they used to be at Manchester. And then that third book is this active distribution networks, where you're making the distribution network smarter. You're bringing in ideas from that transmission system network so that you can, for instance, increase the amount of renewable power in a distribution network. But because this is sort of the current and the future of power systems, we actually pull in a lot of papers from journals like Renewable and Sustainable Energy Reviews, because it changes year on year. And that's where we'll be getting you to do literature reviews on the topic to see where that changes. With that, I will hand back over to Craig. But as I said, feel free to send questions to me and we'll answer them in a second.
Thanks very much, James. I appreciate all of the slides there that you went through. I think most people will find that really helpful and fascinating as well. So the latest slide on James's screen is myself, and my details are there. So if you do have any questions from now until you submit your application form, please do feel free to send them through to me. And if I can't answer them, I'll send them across to James, who I'm sure will be able to. And with that, James, we've actually got quite a few questions that have come through. So I'll start with the first one from Eleanor. She has asked James, what are the schedules for the exams? Are there particular weeks during the course when they will be? And what if it's not possible to attend?
Yeah, okay. So there are 4 exams that you'll need to attend over the 2-year period, assuming you pass everything first time. And we will normally let you know when they run when you've started the course. So you'll be assigned a study advisor who will give you an introduction as soon as you're kind of on the course, before anything started, and tell you, okay, here's your study plan for the 2 years. These are the dates of the exams, and then you can have a discussion to say, well, actually, I can't do this one. Can we move things around? Can I study this thing instead? Can I take a break here? So that you are able to sit the exam. Just as a rough idea of dates, I've just got the notes in front of me. We normally have one late July, one sort of late October, early November, one mid-February, and then one in mid-May. But as I say, the exact timings will differ, and you won't do all 4 of those every year. You'll do 2 in one year and 2 in the other, generally.
Great, thanks, James. Ellie has just sent us a question. She must have lost connection during the part where you were talking about the entry requirement, James. She's asked if I can, or we can point her in the direction of where she can get that. I can send Ellie an individual email directing her to that on the website, unless you have the entry requirements to hand.
Yeah, I mean, I can jump back up to, so the main entrance requirements are here. So first or 2-1 honours degree or equivalent in something relevant like electrical engineering. And what we're looking for is that first or 2-1 level in the relevant units. If you're narrowly kind of below that, as in you've just missed out, there is a slightly alternate entry route where we will assess you after the first 2 units. And I've actually just this morning sat through an exam board where we've looked at that. So if you're just off the requirements here, it's still worth applying. But if you're a long way off, then you're unlikely to get in. But then we will kind of take into account, we'll take more weighting on the industrial experience. Yeah.
Great. Eleanor's asked another question, James. Is there a focus on energy flow optimization for an industrial grid?
Okay, I probably need a bit more detail on what you mean by that.
Sure.
So, okay, I'll try and take a guess, but if Eleanor, if you maybe fill in some more details and post that as another question or a chat. Oh, a site producing their own energy. So actually, we don't focus a huge amount on that. We do have a couple of pieces on the course, a couple of people on the course who are managers of large kind of industrial sites who've come on to look at this. So they've got a local combined heat and power station that sort of feeds back into their industrial processes. But we don't do anything directly for them other than, we talk a lot about protection systems. We'll talk a lot about power system analysis. We'll do faulted analysis. We'll do power flow and things like that, and into modeling, little bits on modeling different devices within a power system.
Great. So Ellie has come back with another question, and her question is, how different is our course from the Renewable Energy Masters program on campus? Yeah,
okay, so there's 2 on-campus courses that you might be referring to here. So there's one that is, sorry, I'll just bring up this one. There's one course called Renewable Energy and Clean Technology. That's on campus only, and that is quite a broad course that looks at policy. It looks at sort of the impact of renewables at the level of an individual house, and that's not just looking at a power system. This course is really about the power system as a whole. The other course you might be referring to is the direct equivalent, which is Electrical Power Systems Engineering, and there's an on-campus equivalent to that. And that we're incredibly similar in that it's the same name and it's the same taught units, and the courses with exams have the same people writing the exam papers. It's a real one-to-one match as you go through. So this is electrical power systems and should match and follow the on-campus course. But there is another one that's called Renewable Energy and Clean Technology, which is a different course entirely.
Thanks, James. Eleanor asked an earlier question. I'm not sure if you did touch on this. It was, how does the course address demand in the developing world?
No, okay, I didn't address that. So there isn't, I'm just trying to think of the detail here. There is a little bit of discussion of it in some places, but there's no kind of focused piece on that. Actually, one of our researchers, one of our professors, Joseph Mutale, that's his area of research and a thing he's really passionate about and interested in. So he's doing a number of projects in that area. And what we'd probably suggest, if that's a particular area of interest to you, is that we pair you up with him when it comes to your dissertation, and then you and him, who's got all that experience in that area, can focus on that piece. But there's nothing in the taught element that, no substantial piece of the taught element that focuses on it particularly.
Great, thanks, James. We've also been asked one, probably a little more around interaction with other students, but one applicant or potential applicant has asked, how can we discuss elements of the course with other students? I think that may go back to what you were referencing before, James, about the study advisor?
So there's for every taught unit, there's a discussion board set up, and actually for the first one, the first unit that you get into, so that you can start interacting and getting to know each other a bit better, that's actually forms 50% of the assessment for the first unit, where I really want you to spend a lot of time discussing these ideas and chatting to the students your sort of colleagues quite a lot, your fellow students. There's then in the final unit, again, so I teach the first and last, and you might see me for some of the others in the middle as well, a couple of them. That last one is a team project, so you actually work together very closely over a 10-week period, and there you pitch a business case to me. So you'll be collaborating quite a lot and using expertise of your colleagues. And there's been some really nice interactions with different people where, you know, you've got people who designed a particular component talking to someone who's using it in the field as a site engineer, and you've got people who are doing the same job in 2 different countries, able to talk. But other than those first 2 units, really then it's down to you to make that connection and keep that connection going. We give you all the tools and ability to do that, and you've got the students with the knowledge. Yeah, and some people get quite a lot out of that.
Great. Another question, James, can I pay the fees in smaller instalments?
Yes, so you don't have to pay the whole fee as one chunk up front. And I'd probably say if the fees, if you want the detail on that, Craig is probably the person to contact to break it down.
Yeah.
But
thanks,
yes,
thanks,
you can pay in installments.
Yeah, just to add to that, James, is you can pay in instalments, and that typically looks like 3 instalments per a year of study that you are on the course. So for the first year, it will be around 3 payments, and then the same for the second year. And I believe it's the same for the second, obviously the 6 months remaining on the last part of the course as well. But if people need further details, obviously James has put my contact details there, and I can get these from the student finance team as well. We have a couple of more questions, James. One is around the dissertation, and how long does that run for, and can they expect to study units alongside the dissertation?
Yep. So the dissertation, nominally, we give people a year for the dissertation, but what we try and do is pick a dissertation topic that is really linked into what you're doing in your job. So for example, if you were, I don't know, a protection engineer working at the distribution system level, and one of your kind of jobs or one of your challenges in work was, well, we're looking at new active management techniques that are going to cause a change to the protection requirements. You're going to have to do that for your job anyway, but actually that's quite an interesting project from a dissertation as well. And if you end up being able to work on this in your job, as you often are, and being able to use data and expertise from your colleagues, it's possible to complete it in 6 months as well, and that's what we're trying to get people to do for that. That's why we say 6 months is kind of the minimum there.
Great.
And in terms of do you study units with your dissertation? No, we really want people to have all of that knowledge of the taught parts before they start. So you'll study one taught unit at a time as you go through.
Oh, great. James, I've got a couple more, probably the last couple of questions, but I think they kind of link in together. One is around the application form and what you might find useful in some of these personal statements if they're discussing their job role or work experience. What is it you're looking for?
Yeah, so I sort of going back to the entrance requirements. What I want in a statement is to see concretely what you've done that links into the taught units. So if you go onto the website, you will see a list of the units that you'll study. And if you look at some of the details in there, you might go, oh, well, I've already done this piece, or this piece is really relevant to my job. Then tell me exactly what you've done and your responsibility. So I think a mistake that some people make when they're sort of filling in personal statements or CVs is just they say, I was involved with this project. I don't know what you did if you just say you were involved. If you were you designed this, or you operated this, or you were were a technician, or whatever it was, tell me the specifics that you did for things that were relevant to this. And that will really help me go, oh, okay, if you've done a load of stuff on power flow or faulted calculations, or you've done kind of transformer sizing calculations, or you're responsible for whatever it is, tell me that. And if you've got a particular area of interest, you really want to study this thing, or you really want to work with this person because you want to become an expert in this niche, this particular area, that really helps me see that you care about the subject and that you want to do well, because you've got a nice clear goal there.
That's great, thanks James, that's really helpful. And it kind of links into, I think the last question I have here is around what, which I might be able to answer as well, is what should you, or what would you expect to be sent in with some of these application forms as far as supporting documents?
Yes, yeah, okay. So we absolutely need a full transcript showing which units you have studied in every year of higher education study. And that, a mistake some people make is if they've transferred from one university to another, they only show us the final year. I need to see everything, and I need to see the grades you've got in every unit. Every university around the world will produce an official transcript that will show that, and that's what I need to see. I'd also like to see the final certificate so I can see the grade that you've got and verify that with the university. So that's sort of the evidence for the first piece. I'll also need to see the evidence for the English language, like your IELTS certificate that's in date, and then a statement from your employer, which will give me the evidence around, or back up your description of your industry experience, saying, yes, this person worked here, this is their role, and yes, I recommend them for this study. That adds a lot of weight to what you've said in your industry experience part. And then on the actual form itself, there's a place to put a statement of, well, why are you doing this course? And you can use that space to highlight particular pieces. I think those are the main pieces that I look at. But there's details as on the form of exactly what you need to fill in.
That's really helpful, James. Thanks very much for that. And I think that looks to be the last question we have received. So thank you very much for your time, James, and to go into such detail in those answers as well for the questions. So I think that pretty much concludes our webinar. Again, if there's any questions that you have after here or during the application process, please do email me on the details James had up before, and we hope to see your applications arrive soon. Is there anything else you'd like to add, James?
No, just thanks for everyone for turning up, and hope to see you on the course soon.
That's great. Thanks very much, James. Thanks everybody for attending as well.
Bye.